Hello everyone, I am Dheeraj Madan. Today we'll be taking a step back and we'll be looking at one of the more traditional algorithms from machine learning, which is Adaboost or adaptive boosting. The idea in boosting is that essentially if you're given some classifier, you construct an ensemble of multiple instances of that classifier, and then you learn an algorithm which combines those instances to be able to give you a combined sort of solution. So essentially the thing is that every classifier may not be performing that well in accuracy, but then combined they are able to do well. So this is the idea of boosting. And essentially in adaptive boosting, the idea is that you learn from the mistakes you have made in the past, and then you give more importance to the examples wherein you committed a mistake, and then you retrain. When you retrain a classifier, you then you do it in such a way that essentially the points wherein you made more mistakes, they are sort of given more importance later. So this is the idea of adaptive boosting or Adaboost. Okay, so let's get started with this. So essentially here we'll formalize first a notion of a weak learner. A weak learner is one, a gamma weak learner more specifically is one wherein the error, the rate of error is upper bounded by, let's say, some half minus gamma, which means that on at max half minus gamma fraction of examples it makes an error, and the rest half plus gamma, they are sort of evaluated correctly. And then the idea is that if you take such a gamma weak learner, how do you combine multiple of these and be able to get a sort of a better classifier. So essentially here we are always looking at the setting of binary classification. So let's get started. So first let's define a notion of weak learner. So more informally, a weak learner is a classifier that makes an error on at max half minus gamma fraction of examples. Training examples. Okay, so let's write down a more formal definition. So in formal definition, we'll essentially be considering weighted errors. Okay, so let's write it down. So basically a gamma weak learner A is such that when given, so what are we given? So essentially this takes in three things. Firstly, a data set capital D of points xi's, yi's. So xi's are inputs and yi's are their corresponding labels. So xi's, they come from some domain set curly x, and yi's are all given by f of xi's. Okay, for some f of xi's in plus minus 1. So f is some deterministic function. So we are assuming that there is a deterministic labeler which has labeled all these examples yi's as f of xi's, and these examples they came from this set, and these were essentially sampled from a distribution curly D. So there is some distribution from which you sample your points, and then you have a labeling function which labels all these points, and this is how you have produced your data set, right? So this is the first thing which is given to this algorithm. The second thing which it takes as input is a sort of a distribution over examples. It's a discrete distribution because we have finite number of examples. So what are the sort of entries in this distribution? So these are essentially pi's, I from 1 to m, such that for all I, pi is greater than or equal to 0 and sum over I, pi equals 1. So we have a weighted distribution over the examples. And third thing is a hypothesis class. So these are the inputs to my weak learning algorithm. Okay, and given these inputs, okay, so given all of these, okay, so it produces a hypothesis H in this class such that 1 by m times sum over I pi, okay, the indicator function that it misclassifies an example xi at xi not equal to yi. So this misclassification rate is upper bounded by half minus gamma. So this is essentially the sort of guarantee which it is producing, right? So given this data set, given a distribution over examples, given a hypothesis class, it picks a hypothesis in this class such that 1 by m times sum over I pi times the indicator function that hxi is not equal to yi. This is upper bounded by half minus gamma. So these are the assumptions which we are making. Okay. So let's proceed ahead. Okay. So the question is this, that can we reduce the error probability of a gamma weak learner? So the original error probability is, half minus gamma to something arbitrarily low. Say epsilon. Okay, so by saying that we are reducing, which means that can we combine multiple of these in an ensemble to be able to get this small enough probability. So what Adaboost does, so what does it do? It successively learns capital T such hypothesis okay, what are these? H sub small t, t from 1 up to capital T, okay, with weights Wt such that for Hx, so basically now there are all these hypotheses and we need to combine them with weights Wt's, and of course these are all plus minus 1. So you can take a weighted sum of these, but then the weighted sum, it need not give me something plus minus 1, so I take the sine function, meaning that if the combined sort of weighted sum is positive, I give a plus 1 value. If it is negative, I give a minus 1 value. Okay, so such that for hx equals to sine of sum over t wt h dx, we have that the error rate, okay, we have that error on these unweighted examples this is upper bounded by exponential of minus twice gamma square capital T. Okay, so this is the assumption, this is the sort of guarantee which is given by the Adaboost algorithm. Okay, so the average error is upper bounded by exponential of minus twice gamma square capital T. So how does this algorithm work? Let's see. So this takes as input. So let's see what are the inputs to this algorithm. The first input is a training set S, which consists of all these examples, xi's and yi's, I going from 1 up to m, a weak learning algorithm to L, and the number of rounds is given by capital T. So how do we start? So first we initialize the weights P1 as 1 by m for each example. And now for t equals 1 up to capital D, we do the following. So we invoke weak learner ht. This is a weak learner on this distribution PT and on the training set S. After this, so essentially you compute your hypothesis, by whatever is the sort of distribution you have, you initialize distribution to be uniform, and then you invoke your weak learner. So weak learner is assumed to give you a hypothesis such that the weighted, assuming your weights are PIs, the weighted error is upper bounded by half minus gamma. Right? So this is what you do. And once you invoke this weak learner, so let's number the steps. So this is the first step, is initialization. This is the second step. This is 2a. This is all inside the for loop now. And then you compute your error. Okay, so this epsilon t you compute as sum over I PIT, the indicator function that h of xi is not equal to yi. And once you've computed this fraction of errors, you can compute the weight of this classifier as half of log of 1 minus epsilon t over epsilon t. So intuition is that if your epsilon t is high, then essentially this weight is going to be low. If epsilon t is low, then this weight is going to be high. Okay, and next you update for next sort of instance, you update your fraction, your importance of each example as exponential of minus yi times sum over s from 1 to d hx xi times yi over summed over all j exponential of minus of yj times sum over s from 1 to d hs of xj times yj. Oh, sorry, yj is already there. Should have called it. Sorry. So this is sum over s, right? So this is hs xi times ws. Right? So hs ws sum is the current hypothesis, and similarly hs ws. So intuitively think of it this way, that sum over s, hsws is my current hypothesis, and if I do minus yi times that hypothesis, this is giving me plus 1 if it does not match the hypothesis, and minus 1 if it matches the hypothesis, and otherwise so it will give me a large positive value if it does not match the hypothesis, and a large negative value if it matches the hypothesis. And by taking a softmax, I am producing a distribution such that the ones which are strictly against the labels which are strictly against the hypothesis, those instances are given higher weight, and for those instances wherein the label strictly matches, or it has a high correlation with the hypothesis, then essentially I give a very small probability to those. So basically I am giving more importance to those instances wherein my current hypothesis is failing badly. And finally we need to output the hypothesis class hx as sine of sum over t wt htx. Okay, so we have the next theorem. Let S be a training set suppose it of V returns with error less than equal to half minus the guarantee which is given by weak learning hypothesis. Of Adaboost is at max 1 by m times sum over I, indicator function that h of xi is not equal to yi. This is upper bounded by exponential minus twice gamma square capital T. So let's try to prove this theorem now. So for each T, denote f of t as sum over p from 1 to t wp hp. Also denote f naught as identically 0. Output of Adaboost is f of capital T, because we need to produce a valid hypothesis which gives plus minus 1 values. Okay. Next we denote z sub small t defined as 1 by m times sum over I exponential of minus yi times f sub t of xi. So what is it doing? So essentially we are looking at the examples and how related they are to ftxi, and the idea is that if you're taking exponential of minus y times any hypothesis, then essentially it's somehow trying to upper bound the error. Okay, so let's make it more precise. So essentially the idea is that so for any hypothesis class H and for any training example x comma y, we have that the indicator function that hx is not equal to y is upper bounded by exponential of minus y times hx, right? And why is this so? Because if y equals to hx, okay, so then basically this indicator function that hx not equal to y, right? So this is equals to 0, and if y equals to hx, then exponential of minus y times hx, since both of these are plus minus 1, so essentially this will just be less than equal to e to the power of minus y times hx, because essentially this is something positive, right? And this is essentially 0, right? So this is going to be less than equal to exponential of minus y times hx. Okay, and actually this is going to be e to the power minus 1, because hx equals y and both are either plus 1 or both are either minus 1. Okay, and if y is not equal to hx, actually the thing is that here ftx, if it is positive, we are taking the sign of that, and when we are saying hx is not equal to y, it essentially means that y is not equal to sine of hx, right? So it's e to the power of anything negative. Okay. Whereas if y is not equal to hx, then the indicator function of hx not equal to y is going to be 1, and this is less than equal to e to the power of anything positive. So that's how these two agree with each other. Now the training error. which equals 1 by m times summed over I times the indicator function that hxi is not equal to yi. This is less than equal to z sub capital T. Okay. So thus it suffices to show, right, why is this less than equal to z sub capital T? Because we have shown that for every instance, the indicator function that hx is not equal to y is less than equal to exponential of minus y times hx. And so essentially if I sum over all these examples, this is less than equal to 1 by m times sum over a exponential of minus yi ft xi, which is essentially zt. Okay. So thus it suffices to show that zt is less than equal to exponential of minus twice gamma square capital T. Okay. So what is essentially zt now? Zt is nothing but zt by z naught. Okay. So if you recall, I defined f naught as identically 0. Okay. Why? Because it's a sum over 0 quantity, so this is by definition 0. And with respect to this definition, I can also define z naught as identically 1. Why? Because z naught, in case of z naught, if I use the definition of f naught, which is identically 0, then each of these terms is 1, and 1 summed over m times is m divided by m, I'll get 1. So z naught is identically 1. So I can write zt also as zt by z naught. And this is for convenience, because now what I'm going to do is that I'm going to open it up as a telescopic product. So it's zt by zt minus 1 all the way up to z1 by z0. Right? Now I have these capital T such terms, and the claim is that, so what's the claim? The claim is that for all time instances small t, what I'm going to have is that z sub small t plus 1 over z sub t is less than equal to exponential of minus twice gamma square. So let's try to prove this claim now. Okay. Okay. So let's try to write down zt plus 1 over zt. Okay. This is essentially summed over I from 1 to m over sum. Okay, so let's write it down first. So this is exponential of minus yi times sum over s from 1 up to t plus 1 ws times hx xi over sum over j from 1 to m exponential of minus yj times sum over s from 1 to t ws hx hs xj. Okay. And now what I do is that I separate out the t plus 1th term from the numerator. So I have this exponential of this particular summation, but then if I take out the t plus 1th term, I'm going to get minus yi wt plus 1 ht plus 1 xi. And then I have the remaining exponential. And similarly in the denominator, I have sum over all j exponential of minus yj sum over s from 1 to t ws hs xj. So if I look at this particular term, right, so this particular thing, right, so this is the probability I'm giving to the ith instance under t plus 1th evaluation, right? So let's read. So if I look at my algorithm again, so this is precisely my PIT plus 1. This is going to be sum over I from 1 to m exponential of minus yi wt plus 1 ht plus 1 xi, right? And then we have pi plus pi pt plus 1 I, right? Okay. Now I'm going to have certain instances wherein yi and ht plus 1 xi are equal, and certain instances wherein they are not equal. So I'm going to write it as summed over I from 1 up to m. Okay, and now I'm going to write it as exponential of so here essentially yi and ht plus 1 xi, they are going to be so on some instances wherein they are equal, and in some instances wherein they are not going to be equal. Okay, so I split this sum into two parts. So the parts wherein these two are equal, I'm going to get a term of e to the power minus wt plus 1, and then I'm going to have pt plus 1i. And on those instances wherein they are not equal, okay, so on those instances I'm going to get a so this is giving me an overall sign of minus 1 since they are not equal, and then there's a minus outside, so I'm going to get e to the power of wt plus 1 times pt plus 1i. Okay, this is going to be e to the power of minus wt plus 1 times if I sum over instances wherein it matches, right? So the sum of all these weights is going to be 1 minus the error probability, 1 minus the classification error, which was epsilon t plus 1. So this is the classification error of the t plus 1th instance, t plus 1th hypothesis. And similarly, I'm going to get e to the power of wt plus 1 times the classification. Now here essentially they do not match, right? So I'm going to get epsilon t plus 1. And now we can even substitute the way we defined wt plus 1. So if you recall, we defined wt plus 1 as half of log of 1 minus epsilon t plus 1 over epsilon t plus 1. Okay. And if I substitute it over here, essentially exponential of minus half of log of 1 minus epsilon t plus 1 over epsilon t plus 1 times 1 minus epsilon t plus 1 plus e to the power of half of log of 1 minus epsilon t plus 1 over epsilon t plus 1 times epsilon t plus 1. Okay. So I'm going to get overall square root of epsilon t plus 1 over 1 minus epsilon t plus 1 times 1 minus epsilon t plus 1 plus epsilon t plus 1 times square root of 1 minus epsilon t plus 1 over epsilon t plus 1. So overall I'm going to get twice of epsilon t plus 1 times 1 minus epsilon t plus 1. So this is how I have computed zt plus 1 by zt, which is twice of this particular value. Okay, and now I know that the error is such that epsilon t plus 1 is upper bounded by how much? So this is upper bounded by half minus gamma. So therefore, if I look at this fraction, okay, so this is less than equal to twice of half or square root of half minus gamma times half plus gamma. Why is it so? Because essentially, okay, so if I look at the function ga equals a times 1 minus a, right? So it looks something like this. It has zeros at 0 and 1, and then there is a maxima at half. So this is essentially monotonically increasing between 0 and half. And so epsilon t plus 1 is somewhere over here, it is less than half, and it's less than half minus gamma, right? So okay, let's redraw it. Okay, So we have this function GA, which equals a times 1 minus a. So this is the value half. This is half minus gamma, right? And this is epsilon t plus 1. So epsilon t plus 1, for epsilon t plus 1 less than equal to half minus gamma, we have that g at epsilon t plus 1 is less than equal to g at half minus gamma. Right? So essentially, we are below half minus gamma. Okay. So what we have is that zt plus 1 over zt is less than equal to twice of half, square root of half minus gamma times half plus gamma, which is twice the square root of 1/4 minus gamma square, which is square root of 1 minus 4 gamma square, which is less than equal to exponential of minus 2 gamma square. So every term, right, in this particular product, every term is upper bounded by exponential of minus twice gamma square. So overall this is less than equal to exponential of minus twice gamma square times capital T. So if I take large enough number of steps, I can reduce this error to arbitrarily low. How is it so? Because if I want this to be less than equal to some value, let's say something delta, then essentially I would want minus twice gamma square t to be less than equal to log of delta, or twice gamma square t to be greater than equal to log 1 by delta, or choose capital T greater than equal to 1 by twice gamma square times log 1 by delta. This will give me a large number of such classifiers such that the overall error is upper bounded by delta. So this is how our Adaboost algorithm, how the guarantee of this can be derived. And yeah, that's it for today's lecture. So and the interesting part is that this classification, we are not even making any assumption on what is the hypothesis class, what is the sort of classifiers we are using. So you can take any classifier and you can combine them in this particular way, and then you can always get this sort of guarantee. The only issue is that you should be able to minimize the weighted sort of errors with respect to the classifier. So that's the overall idea. So that's it for today's lecture. Thanks. Bye.